Thank you very much for the introduction. I'm Zheng from the AND group. I'm going to present PVM, an efficient nested virtualization approach for deploying containers within lightweight virtual machines in public cloud environments. This is a joint work among Alibaba Cloud, the AND group, the University of Texas at Arlington, and Huazhong University of Science and Technology. As cloud computing becomes ubiquitous, containers have gained widespread popularity for building and deploying cloud-native applications due to their flexibility, portability, and scalability. Container technology is also the key to serverless computing and microservice. While containers are lightweight and more efficient than traditional virtual machines, they do not offer the same level of isolation as they share the same OS kernel, opening up doors to a slew of security and privacy issues. Although there has been efforts to enhance container isolation in the OS kernel or design user space kernels, deploying containers in lightweight VMs, such as Kata containers, leveraging VM isolation to address the security vulnerability in containers remain the preferred and widely adopted approach in production systems. These containers and their hosting VMs are often referred to as secured containers. Users can lease bare metal servers or VM instances to host their secure containers and associated lightweight VMs. The latter option with VM instances is cheaper, more flexible, and can scale on the fly. However, it requires nested virtualization, in which users run lightweight VM inside VMs leased from an infrastructure as a service cloud. Before we analyze the overhead of nested virtualization, I will first briefly explain the hardware support that assists single-level virtualization. Without loss of generality, we focus our discussion on Intel platforms. An important issue in CPU virtualization is the handling of previous instruction and the transition between a VM and the host hypervisor. As shown in the left figure, Intel VTX as non-root mode with gas ring level from 0 to 3 to run a VM. Therefore, gas system calls can be directly handled by VM kernel without any involvement of the host hypervisor to handle external interrupts and previous instructions. A VM trapped to the hypervisor and enters the root mode via VM exit. Memory virtualization involves two-level address translations from the guest virtual address to guest physical address and then to host physical address to assist memory virtualization and allow the two-level address translation to be handled entirely by the MMU hardware. Interprocessors allow an extended page table to be registered to MMU and handle GPA to HPA transitions. With EPT, the two-level translations can be handled by VM without help from the hypervisor. Nested virtualization builds upon the hardware support for single-level virtualization and requires additional soft effort. To facilitate the transition among the lightweight VM, which runs containers or L2, the VM instances leased from the cloud hypervisor or L1 and the host hypervisor or L0. Currently, two-level virtualization places both L1 and L2 in the non-root mode. Upon the execution of a previous instruction in L2, a VM access to L0 is triggered. Since the previous instruction needs to be handled by L2's hypervisor, L1, it is forwarded from L0 to L1 by VM entry. After the previous instruction is handled in L1, L1 is unable to resume L2 on its own and therefore trapped to L0 again. Where L2 resumes by VM entry. Note that since L0 must be involved in handling in L2's transition, it maintains VMCS for both L1 and L2, while L1 maintains a shadow copy of L2's VMCS. Compared to single-level virtualization, the transition between L2 and L1 requires traps to L0 hypervisor and costs twice as many row switches as that in single-level virtualization. We define row switches as the switching of both execution modes, for example, from non-root to root mode and vice versa, and address spaces. Nested virtualization is more complicated, But nested memory virtualization is more complicated and incurs even higher overhead. It involves an additional layer of address translation from the L2 guest virtual address to the L2 physical address. Since there are only 2 page tables that can be registered with the MMU, the challenge lies in how to map the 3-level address translation onto the 2-dimensional EPT hardware. The state-of-the-art nested memory virtualization in KVM uses a method called EPT on EPT. This method registers the L2 guest page table with MMU and uses a page table that directly maps the L2 guest physical address to the L0 host physical address, or EPT 02, as the hardware extended page table. The benefit is that if both page tables are properly populated and there are no page faults, address translations are entirely handled by hardware, achieving high efficiency. To construct EPT 02, the host hypervisor needs to compress the other 2 page tables, EPT 12 and EPT 01, into one. EPT 12 is the L1 page table, and EPT 01 is the extended page table for L1. This requires the L0 hypervisor to expose the EPT capability to L1 VM. In summary, VM uses GPT2 and EPT02 to run the L2 VM. Next, we explain how page faults are handled and the 2 phases needed to update these 2 page tables. In the first phase, a page fault in GP2 can be handled entirely within the L2 guest since GP2 is registered with the MMU, fault, fix, return. This phase does not involve any role switches. After a new page is added in GPT2, its corresponding entry in EPT02 needs to be updated, triggering an EPT violation when it is accessed in EPT02. Upon such EPT violation, in phase 2.1, an L0 trap is triggered, and the EPT violation is forwarded to L1 to fix EPT12, as L0 needs to record any updates to EPT12 in order to update EPT02. EPT12 is set to read only. After fix to EPT12, any fix to EPT12 will trigger another trap to L0 for bookkeeping. The first EPT violation only updates EPT12, leaving EPT02 not updated. Next access to EPT02 will trigger another EPT violation and another L0 trap. In phase 2.2, L0 compresses EPT12 and EPT01 to update EPT02. As modern OSs use multi-level page tables, updates to each level needs to follow the above steps. Therefore, in the worst case, when a new page is added to GPT2, there are n plus 3 L0 traps and a total number of 2n plus 6 row switches to complete update both EPT12 and EPT02, where n is the number of levels in the page tables. Nested virtualization is known to be expensive. We ran representative benchmarks to demonstrate how expensive 2-level nested virtualization is compared to a single-level virtualization in KVM. Results show that nested virtualization causes substantial performance loss to some workloads, especially for memory-intensive and concurrent workloads that require concurrent page table updates. The performance difference is up to 2 orders of magnitude. Our analysis reviews 3 issues with state-of-the-art nested virtualization approaches. First, world switches between L2 guest and the L1 hypervisor is expensive. Second, the environment of the L0 hypervisor in CPU virtualization and memory virtualization requires the L0 hypervisor to be modified, not only making the host hypervisor more complex and enlarging its attack surface, but also being a potential performance bottleneck. Third, to support unmodified L1 and L2 VMs, it is necessary to export hardware virtualization support to L1, increasing the coupling between the cloud VM instance and the underlying host hypervisor. Cloud hypervisors are reluctant to support hardware-assisted nested virtualization in their production systems. To address these issues, we propose PVM, a high-performance nested virtualization framework for KVM. The overarching goals of PVM are to first handle nested virtualization within an L1 VM without any hardware or host hypervisor support, making it fully compatible with cloud management. Secondly, to avoid costly access to the host hypervisor, devise fast word switching mechanisms and efficient memory virtualization. As shown in the right figure, the key in PVM is to deprivilege the L2 guest to stay entirely at ring 3 in the non-root mode, so as to let the L1 VM take total control of resource virtualization. PVM is a software-based nested virtualization approach that is as efficient or even more efficient than hardware-assisted nested virtualization. This slide shows the overall design of PVM. It consists of a parallel-virtualized L1 guest kernel, a switcher, a highly efficient piece of assembly code residing in the L1 VM that enables fast word switches, and the PVM hypervisor that handles CPU, memory, and I/O virtualization. Note that the entire PVM software stack is within an L1 VM and can interface any unmodified host hypervisor that supports KVM virtualization APIs. The objective of the switcher is to facilitate the transition between an L2 guest and the L1 hypervisor, as well as between the L2 user and kernel spaces due to system calls, hypercalls, and interrupts. Since PVM does not assume any hardware support, a key component in switcher is per CPU states, similar to a VMCS, which saves and restores L2 guest and L1 host states. During word switches, note that to take complete control over L2, PVM deprivileged L2, both the user and kernel spaces to ring 3 in the non-root mode. In addition to the per vCPU states, switcher also includes system call entries and interrupt descriptor table entries, which are efficiently jump tables that redirect system calls and interrupts to PVM hypervisor for virtualization or emulation. Compared to the VMX hardware support that requires L0 to maintain L2 states, PVM does not involve L0 and handle L2 to L1 transition entirely in L1. Another notable difference and drawback due to the lack of hardware VMX support is that system calls now cannot be handled directly by L2 guest, but need to involve PVM hypervisor. This motivated us to develop direct switch, an optimization in switcher that helps direct a system call intercepted by switcher back to L2 guest kernel for execution. Specifically, instead of directing a system call to PVM hypervisor for emulation, direct switch construct a system call frame, prepare the L2 guest kernel stack and page table to execute the system call, and eventually switches to the L2 guest kernel. The return to user process is similar. Thanks to direct switch, PVM saves round-robin switch to the L1 hypervisor process causes return, again without hardware support. The heart of PVM is a shadow page table approach that handles L2 guest page fault and maintains the shadow page entirely in L1, as shown in the figure. The shadow page table in L1 and L1's EPT are registered with MMU. Since EPT 01 is no different from an ordinary VM's extended page table, the L0 hypervisor is unaware of shadow page table management inside L1. The challenge, however, lies in how to efficiently synchronize GPT2 and SPT12 within L1. Unlike the traditional shadow page table on GPT over EPT approaches, in which GPT2 page faults must first trap to L0 and then forward to L1 to update SPT12, PVM on EPT does not cause any access to L0. There are also two phases of page table updates for every GPT2 page fault. To capture all updates to GPT2, it is made read-only. Upon GPT2 page fault occurring in L2 user space, L2 trap to switcher, where the fault is injected into L2 kernel space for handling. After GPT2 has been updated, L2 return to the switcher via an iReturn upper call and eventually return to L2 user space. The update to GPT2 required n+1 traps to L1 with a total number of 2n+2 word switches where n is the number of levels in GPT-2. Most importantly, this process does not involve L0. The second phase updates SPT-1.2 after completing the updates on GPT-2 and before returning to L2 user space. PVM opportunistically updates SPT-1.2 via pre-fault mechanism. During pre-fault, SPT-1.2 is updated. According to the recently updated entries in GPT-2, the pre-fault mechanism proactively updates SPT-1.2 to avoid future page faults and trap to L1. Eventually, switcher returns to L2 user space as if L2 page fault has been completed. The phase 2 requires one additional trap to L1 and two more word switches if the pre-fault misfires. In these slides, we compare PVM on EPT and the state-of-the-art EPT on EPT and explain why PVM's approach is more efficient, while PVM's approach only saves two word switches compared to EPT on EPT. All its word switches are between L2 and L1, or between L2's usual and kernel spaces with no access to L0. We measure the cost of word switches between PVM's L2 to L1, nested L2 to L1, and bare metals L1 to L0, and found that the word switches due to PVM's memory virtualization are almost an order of magnitude cheaper than that in EPT on EPT, which relies on hardware support in VMX. PVM's software-based word switches are also comparable to that in single-level virtualization. PVM also devises two optimizations for memory virtualization. Please read our paper for more details about the optimizations as well as PVM's approach for CPU and I/O virtualization. Note that these optimizations only take effect within a specific L1 VM and requires no change to the L0 hypervisor. Therefore, PVM allows users to devise customized optimizations without affecting the underlying cloud management. To evaluate the effectiveness of PVM, we first deploy PVM on bare metal server in Alibaba Cloud and use it as an L0 host hypervisor to understand the overhead of software-based virtualization compared to the hardware-assisted single-level virtualization. Next, we run PVM inside an L1 VM instances on Alibaba Cloud to study the benefits of PVM in nested virtualization. We used micro benchmarks and real application to measure the cost of VM access, VM entry, physical performance, cost of page fault handling, and overall application performance, especially multi-threaded applications. We use a set micro benchmark to perform privileged guest operations to trigger VM access and measure the round-trip time until VM entries. The table lists the average round-trip latency under 5 privileged guest operations. The result shows that hardware-assisted single-level virtualization performed the best, which is expected, and PVM achieved comparable performance as a bare metal server hypervisor. In contrast, PVM significantly outperformed hardware-assisted approach in nested virtualization by as much as an order of magnitude. The reason is that for these previous guest operations, PVM costs fewer and less expensive VM access to the underlying hypervisor. This table shows the direct switch improved physical performance. Next, we study the cost of handling page fault. Besides evaluating various approaches, we also study concurrent page fault handling with increasing concurrency. We break down the performance benefits due to individual PVM optimizations. As shown in the figure, PVM significantly outperforms EPT in nested environments. Pre-fault is mostly effective and contributes to PVM's superior performance when concurrency is moderate. Under high concurrency, fine-grained locking, which is a usual customized optimization, contributes most to the performance benefits. Please refer to our paper for more experimental results, including evaluation with real applications. PVM has been adopted in Alibaba Cloud and is currently used to host 100,000 secure containers daily. Since VM instances are significantly cheaper than bare metal servers, there are 36% users who switched from bare metal servers to VM instances due to PVM's close to native performance in a nested environment. To conclude, our experiments in designing and experimenting with PVM found that a software-based approach for nested virtualization can be made as efficient as hardware-assisted approaches, but also offer a slew of benefits, including the support of unmodified host hypervisors and opportunities to deploy customized application-specific applications in L1 VM without affecting other co-located cloud users. This concludes my talk. Thank you for your attention, and I would like to take questions.
Okay, great talk. Again, it's Haibo Chen from Shanghai Jiang University. I'm wondering how do you implement the switcher? Do you assume that there is some hardware mechanism like a VM funk that you can directly switch from one VM to another?
We doesn't use a VM funk because we doesn't want the L0 hypervisor to be involved. Maybe VM funk can be a future optimization.
Okay, thank you.
On the left.
Hello, Masanori Misono from Team Munich. Thank you very much for the talk. I'm wondering what is the main difference between the PVM paravirtualized kernel and Zeng's paravirtualized kernel with shadow paging. And I'm wondering if PVM is doing some specific optimization for container workload.
Ask again slowly. Sorry.
So I'm wondering if PVM paravirtualized kernel is doing some specific optimization for container workload. Does it make sense?
Yes, we deployed secure containers with PVM technology in Alibaba and including the Ant group.
Okay, I think we can talk offline. Thank you.
Thank you for your presentation. My name is Takaaki Fukai from the AIST. My question is also similar to the last question, that what's the benefit of your design compared with the user mode operating system technology, like the user mode Linux or something?
Compared with what?
User mode operating system technology. The example is user mode Linux.
Linux, right?
Sorry?
User mode Linux.
Yeah, user mode Linux.
Okay. User mode Linux is also a software-based, but it uses ptrace-based. Its switching mechanism is very slow. The PVM switcher is built inside the low entry code of the CPU.
Okay, thank you.
Hi, Shaurya Patel, UBC. Thanks for the talk. I was curious about your pre-faulting algorithm. Like, what algorithm did you use and what was the accuracy? Like, are you actually allocating more memory than required so that VMs are consuming more memory because of pre-faulting?
Are you asking about pre-fault?
Yeah.
Pre-fault is an optimization. It is enable default in our production system. And result shows that there are, I don't remember the number, there are a high portion of the pre-fault can work.
But I was curious about the accuracy of the algorithm.
Accuracy, I don't remember the number, sorry.
Yeah, thanks.
Let's thank our speaker one more time.